All right, this is section 9.2. We're going to graph polar equations. So graph the following. We have 5 cosine of theta. Now the rule that I came up with for graphing these is for theta, what we're going to do to pick values of theta, we're going to look at this coefficient right there, which is 1, and we're going to double 1. We're going to take 2 times 1, and then we're going to use that for the denominator of like this. We're going to put in 0 for theta, and then we're going to count by 1/2. We're going to count by halves. 1 times 2 is 2. So we're going to put in pi over 2, 1/2, and then 2/2. And for circles, you only have to go from 0 to pi. So to graph a full circle using polar equations, you only have to go from 0 to pi. Now when you plug 0 in, cosine of 0 is 1, and then 1 times 5 is 5. So we start with 5. Pi over 2, cosine of pi over 2 is 0, so that pi over 2 we're at 0. And then at pi, cosine of pi is -1, so we're at -5. Now, what we could do is plug in thousands of points in between 0 and pi, and we'll come up with a nice circle. But if we know the shape, we only need a few reference points. For example, if I said these 3 points were part of a parabola, you would know exactly how to draw that. If I said these 3 points were part of absolute value, you would know how to draw that. So we're gonna take the same approach with these graphs. We're gonna know what to expect, and then just get a few points for that. So 0 degrees is at 5. 1, 2, 3, 4, 5. 0 radians. And then pi is at pi over 2, pi over 2 is 0. That's the pole. And then pi over here is -5. So really, we only have 2 points, but keep in mind that 5 now is the diameter. So we go 1, 2.5 would be the radius. So there's the center of the circle. Now if we go up 2.5 and go over, try to go straight over to here, about right there, there's half of the circle, like that. And then 1, 2.5 over to here. This should be the other half of the circle, like that. That should be a nice circle. And notice that on this page, I went to Desmos and drew a nice version of this. There's 5. So this would be 3. So 2.5. Let's see, 1, 2, 3. 2.5 is sitting here. There's the top of the circle. This is the center of the circle right here, and you can see a nice version of a circle. So now cosine affects the x. That's why the circle's bubbled off to the right along the x-axis. Now -5 cosine, I just know what that looks like. It has a diameter of 5, 1, 2, 3, 4, 5 over here, and there's a point here at the pole, 1, 2.5, 1, 2.5 somewhere up here, and then down 1, 2.5 over here somewhere, right? So this would be the circle like that. 1, 2, 3, 4. Yeah, I got it. And so that's bubbling off to the left because cosine affects the x, and -x is off to the left. Now likewise with sine, we know that the diameter, not the radius, the diameter is 5. 1, 2, 3, 4, 5. Sine really affects the y. So 1, 2.5 over here, up 2.5, about right there. We got the pole, of course, 1, 2.5, 2.5 here, let's say. And then this, that's a terrible circle, but you get the idea. It's kind of hard to draw circles with these tablets here. I wonder if I could, right here would be the center, and then I would go like that. There you go. That's what it should look like, just like that. And then now that's a positive sign, and then a negative sign would bubble the circle over here. 1, 2.5, right there. So that's what that circle would look like. But it needs to go off up to 5. The diameter would be 5. So there's some nice circles. This is your positive cosine over here. This would be the negative cosine. And notice it goes along the x-axis. And then positive sine up here. And then negative sign on that one. Graph the following. These are limacons, and more specifically, they are cardioids, and they look like hearts. Now, when you graph sine and cosine, they're very circular. So this is these heart shapes are much rounder than your traditional hearts you would see drawn for like Valentine's Day. So let's follow the same rule. Let's look at this coefficient right here, which is 1. We're going to double that, and we're going to count by halves. I know 2 times 1 isn't a half, but we're going to count by pi over 2's. But with cardioids, you have to go from 0 to 2 pi. Circles finish in pi, cardioids finish in 2 pi. So we have theta, and we have the radius. So 0, 1/2, 2 halves, 3 halves, and then 4 halves is back to where we started. So if I plug 0 in for theta here, cosine of 0 is 1, so we start out with 6, 3 plus 3. Cosine of pi over 2 is 0, so that piece becomes 0, and we have 3. Pi, cosine of pi is -1, so there's 0. That means we're going to touch the pole. 3 pi over 2, cosine of 3 pi over 2 is 0, so that's 3. And then 2 pi is back to 1, so we're back to 6. Now let's work our way around the circle and graph the points. So at 0 radians, we're at 6. 1, 2, 3, 4, 5, 6. Pi over 2 is 1, 2, 3. Pi hits the pole 0. I should probably be doing this in a different color so it stands out a little bit more. Then 3 pi over 2, down here is 3. 1, 2, 3. And then 2 pi is back to 6. So now here's what the shape looks like. Like this. And it goes wider than this point. It always goes wider than this point. And then bounces off of the pole. Bounces off the pole. And then goes wide again. That's not very good. But nice and round is what this should look like. So here's a great example of it right here. There's over 6, and notice that when you graph sine and cosine, it's very rounded. So it's not narrow like you see Valentine hearts. Let's try one, and notice that it's bubbled out to the right because we're using cosine. So let me erase a little bit of this. Kind of I want some room here. We're going to do the same thing. We're going to look at the coefficient. That's 1, so we're going to count by pi over 2's. Now this one finishes in 2 pi. All cardioids do. So I have to go from 0 to 2 pi on this. So here's the chart. 0, same chart. 1/2, 2 halves, 3 halves, and 4 halves. Sine of 0 is 0, so this starts out with 4. Sine of pi over 2 is 1, so that's 0. Sine of pi is 0, so that becomes just 4. 3 pi over 2 is -1, so that becomes 8. Because you'll have 4 minus 4 times -1, so that's 4 really plus 4, there you get 8. And then 2 pi, we're back to 4. So 0 is 1, 2, 3, 4. Pi over 2 is 0, hits the pole. Pi is 1, 2, 3, 4. 3 pi over 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. And then we're back to 4. So this bounces, bounce, and it does go wider, like this. Trying, and then it goes wider than this. And trust me, if I'm on the board, I can draw these a little better than that. But this is a perfect version of it right there, nice and rounded, and it looks like a heart. All right, so that's when you have a cosine bubbles out to the right, sine bubbles down because it's negative. So you should have somewhat of an idea of what these are going to look like before you graph them. So there's some nice graphs of those. Let's see. How about limacons with an inner loop? These graph from 0 to 2 pi. Let's start, and we're going to look at the coefficient right here. We're going to double that, 2 times 1. And we're going to count by 1/2. So that's going to be count by pi over 2's. We have theta and we have r. So we're going to go 0, pi over 2, so 1/2. I was going to say 2 halves and I wrote 2. I don't want to do that. So 1/2, 2 halves, 3 halves, 4 halves. Let's plug 0 in for theta. Cosine of 0 is 1, so we get a negative 1. Now notice on the r's on these, we didn't get an r that's negative. Did not get an r that's negative. Even on circles, did we get an r that's I think we did on circles, but we don't get an inner loop with circles. Where am I at? Here we are. Cosine of pi over 2 is 0, so that's 2. Cosine of pi is negative 1, so there's 5. 3 pi over 2 is 0, so that's 2. And then 2 pi is 1, so that's we get to the negative 1 again. So at 0 radians, we're back at negative 1 here. Pi over 2 is 2. Pi radians is 5. 1, 2, 3, 4, 5. 3 pi over 2 is 2. And then 2 pi is back to negative 1. So here's what this looks like. We should probably start over here. We're going to go a little wider than this. And instead of bouncing off the pole, this is going to go through the pole. We're going to go through that point, which creates the inner loop, and through the pole again. Now it goes a little wider. It's going to go through this point a little wider, and then finish where we started like that. So that's what the inner loop should look like. And there it is. There's a nice, very nice version of it. Theta r. We're going to look at this coefficient right here. That's 1. So 1 times 2. We're going to double that. And that's what we're going to count by. Actually, the denominator. So we're going to count by pi over 2's again. 0, 1 half, 2 halves, 3 halves, and 4 halves. We plug 0 in. Sine of 0 is 0, so that's 3. Pi over 2 is 1, so we get 8 there. Pi, sine of pi is 0, so that's 3. Sine of 3 pi over 2 is negative 1, so that's negative 2. There's where we're going to get that inner loop. And then 2 pi is 0, so that's 3. So 0 is 1, 2, 3. Pi over 2 is 1, 2, 3, 4, 5, 6, 7, 8 up here. And then, did I count wrong on that last one? I needed 8 right here. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I need to go out here. I counted. I was off by 1. All right, where are we at? We're at, we did 0, 3. Pi over 2 is 8. Pi is 1, 2, 3. 3 pi over 2 is negative 2 up here actually. And then 2 pi is 3. So maybe we should start here. And it looks like circular. But instead of bouncing, it goes through. There's the inner loop. It's going to come around here. And that's way too sharp. I drew it way too sharp because these are graphed much rounder than that. There's a great version of it, of course. And there it's crossing at the 3's. There's the negative 2, and up here at the 8. Inner loops. You get a negative r, you're going to have an inner loop. How about dimpled? Let's look at what dimpled is. We're going to follow the rule again. We're going to multiply that coefficient by 2, so we're going to count by pi over 2's. These also graph from 0 to 2 pi. Everything graphs from 0 to 2 pi except for those circles. And then some roses that we'll get into on our next class. So we have theta here and r. 0. 1 half. 2 halves. 3 halves. 4 halves. Plug 0 and cosine of 0 is 1, so we get 1. Pi over 2, let's see, cosine of pi over 2 is 0, so we get 3. Pi is negative 1, so that's 5. 3 pi over 2, cosine of 3 pi over 2 is 0, so that's 3. And then 2 pi, cosine of 2 pi is 1, so we get 1. Now notice there are no zeros and there are no negatives. That means that this graph will never touch the pole. It won't cross through the pole either. So 0 is 1. Pi over 2 is 1, 2, 3. Pi is 1, 2, 3, 4, 5. 3 pi over 2 is 1, 2, 3. So it's going to go circle out like this. And it'll be dimpled. Boing. It's going to bounce off that point rather than bouncing off the pole. Go through that point and then come around. That should be nice and symmetric. Of course, I have a nice version of that here. what? Did I graph it wrong, or is that what's wrong here? Cosine of 0 is 1, so that's 3 minus 2. Did I type in the wrong equation here? I think I did. I think that's backwards. This is backwards. But it should bounce off of that point here, except over here. I think I typed in the wrong equation for this. Anyway, this is correct. That other one is not. The point is it's nice and rounded. All right, let's try this one over here. Theta and R, 0, pi over 2 pi, 3 pi over 2, 2 pi. Let's plug 0 in. Sine of 0 is 0, so we get 4.5. Pi over 2, sine of pi over 2 is 1, so we get 1.5. Plug in pi, sine of pi is 0, so that's 4.5. Sine of 3 pi over 2 is negative 1, so that's 7.5. And 2 pi is 0, so we get 4.5. So 1, 2, 3, 4.5. Pi over 2 is 1.5. Pi is 1, 2, 3, 4.5. And 3 pi over 2 is 7.5. 1, 2, 3, 4, 5, 6, 7.5 right there. So it's nice and rounded like this. Boing, bounces off that point because it's dimpled, and then round like that. Let's see if I type this one in. Yeah, that looks good. This one I missed a negative sign or something. Convex. If this number right here is twice or more this, then we're going to have a convex. It's not going to be dimpled. But we follow the same rule. We just have to know that this is twice or more of that. So we have theta and r. Let's see. We're going to count by pi over 2's, 0. Pi over 2, pi. Here's 3 halves, and we have 4 halves. Let's plug 0 in for cosine. That's 1, so we have 7. Pi over 2 is 0, so that's 5. Pi is negative 1, so that's 3. Because you'll have 5 minus 2 when this is negative 1. 3 pi over 2 is 0, so that's 5. Then 2 pi, we're back to 7. 1, 2, 3, 4, 5, 6, 7. Right there. Pi over 2 is 1, 2, 3, 4, 5. Pi is 1, 2, 3. 3 pi over 2 is 1, 2, 3, 4, 5. And then we're back to 7. So again, we got this nice rounded. And now it's going to go convex. It's not going to bounce off of it. It's going to go through it, and it's going to have a little bubble on that point right there. It's going to bubble out. And of course, I have a nice version of this. It's convex. It's not bouncing off of it. It's not a dimpled one, convex. So over here, same thing. And what you notice about this process, it's the same thing over and over again, especially on this first day where all of the coefficients are 1 there. So 1 half, 2 halves, 3 halves, 4 halves. So we plug 0 in. Sine of 0 is 0, so we get 6. Pi over 2 is 1, so that's 4. Pi is 0, so we got 6. 3 pi over 2 is negative 1, so that's 8. And then 2 pi is 0, so we got 6. So 0, 1, 2, 3, 4, 5, 6. Pi over 2 is 1, 2, 3, 4. Pi is 1, 2, 3, 4, 5, 6 over here. And then 3 pi over 2 is 1, 2, 3, 4, 5, 6, 7. I think 8's all the way out here. And then 2 pi is 6. So this is rounded, very rounded, very rounded. Goes through that point, but it's convex. It doesn't bounce. And then rounded like that. And this tablet. So I knew it would be tough to draw these with this tablet, but this is what it should look like. More of, quite circular, right? But convex at the top.